We are live on YouTube now. Oh, I see that Surya has joined.
Yeah. Should we do a quick check or?
Sure. Sorry, Mikhail.
Do you want to unshare? Yeah.
Yeah, if you could just to.
No problem.
Hi, Surya. Can you try put up your slides real quick because we need to start session in 1 minute?
Okay.
It's just for check. It's just to check that everything works with screen share.
Okay. Where do I screen share from? Sorry.
Should be at the bottom of the.
Okay, got it.
Great.
Does it show in full screen?
Perfect. Looks
Yeah,
great.
perfect.
Thank you.
All
So we
right.
can go back to Mikhail then.
I cannot, I think.
So thanks, Surya. You may have to
unshare?
end your.
Yeah,
Yeah.
Surya need to stop sharing.
Sorry.
Mhm.
Great.
Oh, doesn't. Oh, okay, good. Yeah.
All right. Well, welcome everyone. If you're just joining us, this is the session on mathematical theory of deep learning for ICMNS 2020. And just to orient you briefly, if you have a question, you can submit it on the Q&A panel. That's different from the chat. I won't be monitoring the chat, so use the Q&A or the Slack channel to post your questions. And you can also upvote or downvote them so that we can get a sense of which ones I should pose, and I'll pose them at the end of the talk. So our first speaker today is Professor Mikhail Belkin, just moved to the University of California, San Diego at the Data Science Institute, and he will be talking about from the bias variance trade-off to double descent. Take it away.
Thank you, Andrew, and thank you very much. So I would like to talk about some new things that have happened and trying to understand deep learning, and in particular to the specific ways that we are learning from deep learning, the new phenomena that we're trying to understand based on the practice of deep learning. I actually kind of find it very useful to think about it in terms of the lessons of deep learning, is that by looking at the practice, we can understand, try to see what is it that we need to understand and how can we approach. I'll talk about two lessons today, really only lesson one with regard to statistics, what we need to understand about statistics from the practice of deep learning. Very brief, I mentioned the lesson two, optimization. And the common theme of what we're observing, and at least what out, will be this idea of overparameterization and interpolation. So let me start beginning, and I will just very, very briefly. What do we do in machine learning, right? We have input data, xi, yi, and we would like to, based on this data, predict data that we haven't seen. So we would like to construct a function from the feature space to the output space, maybe just -1 and 1 to be really simple class problem, that best generalizes. And what does generalization mean? Well, under the simple assumption when data is chosen IID, you can simply say that the best statistical predictor is the function which minimizes the loss of unseen data. Now, of course, to minimize the loss of unseen data, we have to have access to the unseen data, which is by definition is not possible, right? Since we have a forth. So what do we do in practice? Well, in practice, more theory, we consider the empirical risk minimization. What is empirical risk minimization? We choose a family of functions, and we try to choose a function from the family which minimizes the loss on the training data. So instead of unseen data, we take the training data, which is the data we have seen. And instead of choosing all functions in the world, we choose functions from some family of functions, like neural networks, for example, of certain architecture. So you can see the goal of machine learning and the goal of empirical risk minimization are very similar, but not quite the same. Importantly, there are important differences. Now, let me very briefly describe the classical view. So what I'm going to do, I would like to describe the classical view of this, and then I would like to show why this classical view in some sense is unsatisfactory. And then I point out to this kind of new ideas which will help to explain what we observe. So the classical view of this, and a lot of it is due to Wapnick, it's described very nicely in his book, Statistical Learning Theory, is that the theory of induction, as he calls it, is based on the uniform law of large numbers. That's one. And effective methods of inference must include capacity control. So to unpack this, what is uniform law of large numbers? Uniform law of large number simply means that for my class of functions H, empirical laws for any F, this class of functions, approximate the expected loss of F. That's exactly a uniform law of large numbers. That's one. Now, what is capacity control? Capacity control means that H must contain functions that approximate F star. If F doesn't have functions which approximate F star, this is kind of a doomed enterprise, right? If in your class of functions there are no good functions, then there is no point doing this at all. Now, it is easy to see that if you have 1 and 2 together, then the loss of the empirical optimal and the loss of the true optimal will be similar. That's kind of the main result of this line of investigation. To connect the loss of F star RM of F star. And of course, if we can find a function like that, F star RM is good, because it's close to the best. Well, what about uniform laws of large number? To unpack this a little bit more, uniform law of large numbers work like this. You have inequality, which you may call WYSIWYG. What you see is what you get. So this inequality is of the following form. On the left, you have the expected risk. This is the risk of unseen data. This is what you get. On the right, you have the empirical risk. This is what you see, right? This is a loss on the data that you have. And the inequality works as following. It says that what you get is bounded by what you see, plus some sort of model complexity term, which is either a model or function complexity. There are many, many versions of this, hundreds probably. So that is uniform loss of large numbers. Now, what about capacity control? Capacity control, according to Wapnick, works as following. You increase the capacity of your function space, and when you increase the capacity, of course, you can fit the data better because you have more functions to fit the data. So empirical loss goes down, empirical risk decreases. But the second term, this model complexity term increases because the model complexity goes up. So one term decreases, the other term increases. And the idea is to find the point where there is kind of the optimal, the bottom of this U-shaped curve, by making them roughly equal. That is the goal, to find this bottom of the U. The way it's done in practice is usually something like that. This is kind of a heuristical reinterpretation. This is from Elements of Statistical Learning by Hasty, Shirani, Friedman. As you increase model complexity, the training loss decreases, the test loss decreases, and then goes up again. On the left, you have underfitting. On the right, you have overfitting, and the goal is to find the sweet spot, the bottom of the U. And a kind of corollary to this is that the model with zero training error will generalize poorly. But the bottom, the model with zero training error is on the right end of this diagram. We call it interpolation just for future use. Mathematically, it fits the data exactly. But so very recently, actually, the evidence for this is much older than that, but I think recently it became much more clear that this story has some problems. And there's kind of a very nice example from Zhang et al. They did training of a neural network on CFAR10. They get 100% train accuracy. And you can see that even though train accuracy is 100%, test accuracy is still very good. It's almost 90%. So you don't actually see much overfitting. Well, on its own, this is not quite enough, because you may still see, well, 90%, maybe it's still all right. You cannot quite say, but this is that there is no overfitting, but this is very suggestive of it. And to somehow see it more exactly, we did the following experiment. This is joint work with Sivan, my student Sivan Ma and Suvik Bandal. What we did, we randomized the labels for, so this is feminist, it's a 10 class 100-digit data set. We randomize the labels for it. So on the x-axis, you have the level of randomization of the labels. So there are 10 possible classes, it's 100 digits, right? 1, 2, 3, 4, and so on. For say 10, 20, 30, and so on % of the training labels, we just assign a random. Okay, and we do the same way for test and train. Now, this becomes a very noisy data set after you randomize so many of the data points. And you can see that the green line here, let me just ignore the rest of it. The green line here is the base optimal. You cannot, if 10% of your random of your data are random, you cannot do much better than 10%. That's just not possible. They're random, right? You cannot predict them. So the green line is the best optimal. It's theoretically better than the green one. 90% is random, because if you just choose them at random, you will have 90% error rate. Now, what you see is that this red line, which is Laplace kernel machine, it doesn't matter exactly what it is, but neural networks behave very similarly. The purple line is neural network. And you can see, even for very high noise levels, it's not that different from the green line, even for 70 or 80%. Much better than random. Now, what is this training machine? What is this Laplace kernel machine? It's actually trained to have 0 training loss, not just accuracy, actual loss, it's square loss. So it fits the data exactly. It exactly interpolates mathematically up to numerical accuracy. And even though it fits this noisy data, it still does fine, right? No problem. I mean, it's slightly worse than the optimal, but it's still much better than random guess. So what is the implication? The implication is that this type of behavior is very difficult to explain from the point of view of usual generalization bounds. Why? Because this loss is not the training loss. That means that test loss must be directly bounded by the model complexity. But this is very problematic. Why? Because, well, if you look at this, if you look at the level of, say, 70% label noise, you will see that bound cannot be built, it would be wrong. It cannot be above 90% because it would be trivial. So if you want to have a bound which is non-trivial and hopefully correct, it has to be between 0.9 and 0.7. And presumably as n goes to infinity, that should hold. Now the problem is that first the constant, this constant has to be exact, and we don't really have bounds, well, unless some very, very special cases, we don't have bounds with exact constants. Usually the log factors are all sorts of other things there. Second, how would quantity under the square root even know what the correct level is? Because the correct level, it has to do something with the Bayes risk, right? It doesn't have this detailed knowledge about the problem. And classically, this is handled by the fact that you have empirical loss. Empirical loss has the knowledge about the Bayes risk, but in this case, we don't have empirical loss. So that's kind of what you can say, is that first, there are two things. First, empirical finding is the goal optimization. Interpolation unexpectedly aligns with goal of machine learning, minimizing the loss. And this is unexpected because I don't think, like, somehow fitting noisy data exactly seems like a wrong thing from a statistical intuition, but yet it seems just fine. Even very noisy data, like with 70% noise. And clearly the bounds that we have cannot account for generalization on the interpolation when data are noisy. Now, so that may be like this kind of the first lesson of deep learning. And it's a lesson of deep learning, but it doesn't just apply to deep learning. In fact, what I showed you was a kernel machine. It wasn't deep learning method at all. But similar empirical observations, of course, hold for that. The theory of induction for learning cannot be based on uniform last numbers in capacity control. We need a different paradigm. We need a different set of techniques. And I'm going to, we don't have a complete theory for this yet, but we have at least some ideas of where it should go. So that's what I'm going to talk about next. Okay, now let me point out that there is one classifier for which we know it interpolates and it does okay. And it's the simplest one. It's kind of funny, you know, like nowadays, I think when you ask people, okay, what's the simplest classifier? And, you know, people think about neural networks. No, actually, the simplest classifier is one nearest neighbor, right? It's just prototype learning. You have your data, you have a new point, you just find the closest one, right? That's, I would say this is the simplest. And the interesting thing, it's an interpolating classifier because you, for each example, right, you assign the same label to it. So it's an interpolating classifier. It's really simple. And it actually had a theoretical guarantee. It's twice the base risk. It's a classical result due to hover and hard. Now, of course, it's not optimal and it's very far from optimal because instead of the optimal rate, you get twice the optimal. So instead of 10% error, you will have 20%. Pretty far. It turns out that there is a way to actually have something like nearest neighbors, which is optimal. And this is related to something called Shepard's interpolation. It's some sort of interpolating nearest neighbor scheme. I should point out this is joint work with Daniel Su and OverParameterize, the follow-up on statistical optimality with Sasha Raklin and Sasha Tsibakov. And basically the idea is if you take a weighted nearest neighbor scheme, and the weight is such that as you approach a point, it goes to infinity. So it's like inverse distance weight. Then this becomes an interpolating classifier, and you can prove that it is optimal in the sense that it converges to the optimal in the limit of infinite data, and in fact, even the rate is optimal. So it's fairly strong sense optimal for regression and classification. Well, the minimax rate is for classification. I'm sorry, for regression. Okay, I see there was a question.
I think we can hold it for the end if you're fine with that.
Oh, that's yeah. Then what do we have? If you look at this blue curve, so what do I have on this picture? Just to give you an idea what is happening. My data, which are these little circles, are sampled from the blue line plus noise. So it's a linear model, right? Linear plus noise. And of course, the blue line is the best possible. If you know a priori what it is, you should do blue line. What does this method give? It gives you this red line. And the red line goes through every data point. So you can say, okay, this is crazy. I'm fitting all this noise exactly. But actually, if you look carefully at it, you see that it's not really a big deal because even though at every data point you are far from the blue line, on average on this line, you're actually pretty close. So this is kind of a remarkable thing, right? You're at every data point, you're really doing badly, but between those data points, you're doing okay. And this is kind of a visualization of the theorem. You can prove that this is optimal in the limit. It's the data because so. So at least it's not optimal in some sense and also interpolated. But of course, that's not what we do in practice, right? This is not the kind of method which is commonly used in machine learning. What people use? Well, people use, nowadays it's a lot of it is neural networks. So what about neural networks? And the neural networks, I think, have this remarkable property that it's very easy to decouple the number of data points from the complexity of the model, right? Complexity of the model has nothing to do. It's a purely architectural choice. You put, okay, I have 1 million parameters or 1,000 hidden units or something like that. It has nothing to do with the number of data points. And what you realize is that when you increase complexity beyond this point of interpolation, beyond where you have enough to fit the data, something really interesting happens. So up to the point of interpolation, you are tracing this classical U curve. But you're doing very badly at the point of interpolation, this kind of interpolation peak. But the amazing thing is that once you go beyond the point of interpolation, this drops again, and often drops indefinitely at all asymptotes to infinity, to something. No, not to zero, of course, it cannot, but to some, relatively good number. And frequently, but not always, this kind of infinite point is better than the bottom of the U. So we call this double descent, and we really did quite a few experiments for random forest, for neural networks, for boosting, and for other things. It seems to be a very consistent, robust phenomenon. And I should point out that other people also observed this effect, and including Andrew, and in particular, Advani Sachs they observed it for linear models, and Spiegler et al. For some certain types of neural networks. And so it does seem to be fairly general, quite general actually, at least as general as a U-curve, I would argue. Now, I would like to, I don't have a lot of time, so what I would like to do, I would like to maybe just give an example of what it looks like in one dimension, so you can kind of visualize it. So imagine this, I have one-dimensional data, this red point, and I'm building a very simple one hidden layer neural network. I don't want to describe it since I don't have time. So with 3 neurons, you get kind of fit like this piecewise. They're always piecewise linear because they're rarely with 30 neurons, and this is reasonable fit, right? This is like a good parametric fit. With 30 neurons, I get classical overfitting, right? It goes crazy, which is you would expect. But the amazing thing with 3,000 neurons, right? It looks nice again. And in fact, you cannot even tell that it's piecewise linear. This is actually a piecewise linear function, but because there are so many linear pieces, it looks smooth. And of course, if you do 3 million, you wouldn't be able to tell the difference between 3,000 and 3 million. It looks essentially the same. So this is a true non-parametric model in a sense. Even though it's parametric, it's kind of not parametric because 3,000 and 3 million makes no difference. Okay. Now, I should say that we now have a bunch of analysis in various settings, and in the last maybe year or two, basically showing that this really does happen, at least for linear regression in certain settings, we can prove it and we can analyze it precisely. And there is a lot of evidence that for neural networks, this is really what's happening. This is not proved for general neural networks, but there is, I think, prevalence of evidence for that. Now, I would like to say that this, in a sense, you can view it as a different framework for modern machine learning. By modern machine learning, of course, I don't mean technically just modern machine learning, but the kind of overparameterized learning that is used now. It goes, you have to look at history, it goes, of course, back. And basically, it's a principle of Occam's razor, right? What is Occam's razor? Occam's razor is, you choose the simplest explanation which fits your data. And in this case, you can kind of say, fitting the data is just interpolating, right? That's perfect. That's exactly fitting your data. And what is the simplest? Well, the simplest is some sort of inductive bias. And usually in these settings, this is some form of smoothness, and the smoothness can take different forms. It can be explicit in terms of minimum functional norm. And this is the way it's done for kernel machine. It can be implicit through optimization. Or it can be by some sort of averaging, when you take some trees and you average them, and the resulting average tree is smooth. It's a kind of form of banking. The resulting tree is smoother than any of the individual tree because you average. And I think there is something interesting for kernel machines for those who are familiar with that, because all the things can be shown to coincide, which is, I think, really remarkable. Okay, so I think I'm going slightly over time, but I think I'll talk about, let me kind of summarize what I said, and then I'll say like maybe 1 or 2 minutes on optimization. The landscape of generalization, as we understand it now, on the left, you have this classical analysis where what you see is what you get bounds apply. On the right, you have this modern interpolation regime based on deductive biases, and we're now seeing first analysis of this. And I think one remarkable aspect of this is that overfitting now, as we understand, is not directly related to just fitting the data exactly. It's actually a band of parameters in this kind of landscape. So that's, I think, one very specific different view that we need to take from this one specific lesson. What is overfitting? Overfitting is not what we used to think it was. Okay, now I'm going to just very briefly say something about optimization, and it's a separate discussion, but I do want to point out that there are lessons for optimization as well, and I think those lessons are also quite important. What is classical optimization? Classical optimization is that non-convexity is bad. There are many local minima, no general global optimization technique. And usually the picture is drawn as something like this, right? You have a bunch of local minima and you don't know how to choose one. This picture is deeply misleading for OverParameterize system because it actually kind of implies local convexity at each of the minimum. And also it implies that somehow this minimum are separate. The picture we should really think about is this one, and this is from our work with Leo, Lim, and Joe, my students. This is the landscape. That the landscape, really, you have a family of global minima which form a band. And in some sense, this is quite different because you can see this landscape actually not convex. It's not convex in any neighborhood of any point. And you can see it, well, I don't have time to describe, but you can see it. If it were convex anywhere, locally it would have to be a line, but it's never a line. There is curvature to this curve at the bottom. So we really cannot think of convexity, even locally. It really has to be essentially non-convex. It turns out that we have a set due to Pollack and Lyasevic originally in 1993. There is Pollack-Lyasevic inequality, which implies convergence of gradient descent and convergence of local depth. So we do have tools, but these are not the same tools as convexity. So we have to get away from that. Okay, so let me summarize. On the left, we have this classical model. Careful parameter selection is required to find this bottom of the U. Many non-global minima, and there is local convexity at the solution. In the modern model, we have this good generalization from inductive bias, and it's not sensitive to the number of parameters, not so much, right? If we move left or right on this curve a little bit, it doesn't make a huge difference. So that's, I think, what we observe in practice. Basically, taking a very large system often just works, and you don't really care how large as you basically can fit into your memory. So, and all minima are actually global minima. So finally, let me finish with it's a neuroscience conference. I would like to say at least something conjectural about neuroscience. And that I think we're now we're seeing some new mechanisms, but we're starting to get some new understanding in machine learning of these mechanisms, both for statistical and optimization. And the question is, well, can this serve as a basis for biological learning? And I think, I'm not an expert in neuroscience, and so take this as a pure conjecture, please. But I think this makes sense because this makes somehow a very robust, right? We don't care how many parameters we have so much. We don't, it's just some local update rules. They just seem like a very reasonable mechanism for a biological system to have. And, you look at the human brain, well, there are tons of neurons there, right? There's something like 100 billion neurons and 10 to the 14 synapses, right? So why can't it? I mean, I'm not saying this is actually what happens, but at least on the surface, it wouldn't be absurd to say that maybe something like that is happening. We have enough somehow. We would do some sort of updates, some Hebel rule or something, I don't know. And maybe some of this mechanism can actually work biologically. So maybe I'll stop here.
Thank you. Fascinating talk. So I'll pose a few questions from our audience. The first is from Tatiana Engel. She asks, if we fit noise in the data exactly, would this lead to good generalization performance, but bad behavior on adversarial examples? So I guess, is there a relationship to adversarial robustness in your view?
Absolutely, yeah. That's an excellent question. In fact, we discussed it in this. Let me just go very quickly. We discussed it in that paper, in fact, specifically. It provides a mechanism for adversarial examples. Like if you look at the graph, you see that it will have tons of adversarial examples, right? And what you can show is that if you fit your data exactly, as long as the labels are not deterministic, so as long as there is any noise in the labels, you will always have adversarial examples. And I don't think this is the only mechanism by which adversarial examples arise, but it is certainly very, very consistent as well, right? That for architectures for different things, it's adversarial examples.
All right, so maybe I'll smush the last two together so you can answer them in one go. I think that the broad question is, you've shown that models can generalize well, but they may not recover the underlying low-dimensional model that generated the data. So is that a reason we have to be careful in even comparing these models or using them in neuroscience? Because you could get a system that fits the data but doesn't reflect the generative mechanism.
Absolutely, yeah. I think this is an important distinction. Somehow, when you're doing, I think there is maybe this is a different paradigm almost, because you see in science, right, you want to identify one thing or a small number of things, and you say, these are my controls, right? Like physical laws, they don't depend on a lot of things, right? Like the gravitation force between two objects is inverse proportional to the square of the distance. It's simple. So in science, neuroscience, and other things, we would like to identify a few parameters and say these are the important things. I don't think these models can do that. They really don't identify that. So if you know the mechanism, if you know something about the mechanism, I think you still have to use that mechanism. What they are saying is that in the lack of knowledge or in the very weak knowledge about the things, we can throw a bunch of features which only weakly correlate with what is predicted. And that's okay, that's good for prediction, good enough. But I don't think it has explained, so that's why I'm a little bit skeptical of the attempt to extract the actual laws from neural networks, because I think they have strong predictive power. Doesn't mean that they encode the actual laws, the actual scientific knowledge in them. So really, I think we have to separate.
All right.
I feel there are separate modes of inquiry.
Great, yes. And there are more follow-up questions on Slack if you have the chance to go look at those. So thank you very much. I think we have to move on to the next speaker.
Thank you.
All right, so next up we have Surya Gunasekar, who's a research scientist at Microsoft Research. And she will be talking to us about kernel and deep regimes and overparameterized linear models.
Thanks, Andrew, for the introduction, and thank you all for attending the talk. And I should also thank Misha for setting up much of the introductory material for my talk too, so I can go into details much more clearly. So today I'll be talking about kernel and deep regimes in overparameterized linear models. I'll explain all these terms as I go along the talk. Okay, so here again, the goal is to understand how, from a mathematical understanding of neural networks, or more scientifically grounded understanding of neural networks, by going through examples which are simple to analyze and trying to extrapolate the properties we see in simple models to more complicated neural networks. So just to take a step back, if we look at most of the deep learning used in practice today, they are often very large neural networks trained on very large scale data set. And a key component of most of these neural networks is some form of loss minimization over observed examples, over using variations of algorithms like gradient descent. So this, as Misha set up, a classical ML problem is just empirical risk minimization. So you have a data set of observed examples and you minimize the loss over the observed example over some function class. And typically this function class is parameterized. And throughout this talk, I'll denote the parameters by W. If there are variations, I'll mention them. And so coming back to neural networks itself, so in classical machine learning, as Misha initially alluded to, if we have, in classical machine learning, we work in what is called an under-parameterized regimes, where the number of degrees of freedom for these function class, or the number of parameters, roughly speaking, is much smaller than the number of examples. So the law of large number kicks in, or uniform convergence bonds kick in, and we know that minimizing the empirical loss is all we need to care about. And once we have a good solution for empirical loss based on the theory, we know that we'll have good generalization properties to unseen examples. But today's talk will focus on what is called as OverParameterize model, or this is equivalent to what Misha calls as interpolating models, where typically the number of parameters is much larger than the number of examples. So I wouldn't read too much into this exact numbers, because often the effective dimensionality of the parameters is not exactly like the number of parameters. But a more functional way to think about what an overparameterization regime is to consider this empirical risk minimization loss. And throughout the talk, I'll call something overparameterized if this empirical loss has multiple non-equivalent global minimizers. So what it means is that this loss, whatever it is, has many solutions which perfectly fit the data. All of these are global minimizers of this optimization problem, if I just see it purely as an optimization problem. But on the other hand, most of them will perform poorly on an unseen example, even though they are global minimizers of these empirical risk minimization objective. And specifically from a generalization point of view, and also from like robustness and other things we typically study in this point of view, this creates a problem because we have solutions which are not equivalent. So this learns very different solutions, all of which are global minimizers of this problem. But we don't know, I mean, the optimization problem itself doesn't tell us what kind of functions to look for. An example would be to fit a linear model through, fit noisy data around a linear model. And if we didn't constrain the model class, we can get all kinds of overfitting problems, and also all kinds of good models in the span of all functions. And the goal is to find out like why, even though neural networks work in this kind of unusual or ill-posed regime, why do we still have good performance on new examples? Because in practice, we do take these kinds of overparameterized models and use some variants of stochastic gradient descent to minimize these losses. And the solutions we end up with, like subject to a lot of bells and whistles and a lot of fine tuning, does have good performance on new examples. And we want to get into the core of this. And that is a problem I've been studying for the last few years, which is to understand what kind of functions are learned by stochastic gradient descent, specifically gradient descent, when minimizing overparameterized models. And although this is much more prominent in deep learning setting, like one can perceive there are such examples even in linear models. And much of the past theory we have built up, with of course a few exceptions, have been on versions of linear model, which already give us quite a good understanding of the problem. So just to summarize the results which have been known like by end of 2019 or something by our group and a bunch of other groups. So we started studying this problem in the context of matrix completion or matrix factorization or matrix sensing, where you have an underlying ground truth matrix we want to estimate, and we observe, like say matrix completion, taking matrix completion as an example, we observe some of the entries of the matrix. And in a more general setting, you take some linear combination of all the entries of the matrix. So Xn here denotes some linear measurement matrix, and your underlying matrix I'm representing as U times B. U and B are some lower typically lower dimensional matrices. So U times B is a full dimensional matrix, and we observe some of the entries of the matrix, and we want to do a minimization over U times B. And typically we write it in this factorized formulation to ensure that we achieve something called a low rank constraint, which is assumed or like hypothesized to be useful for many of these matrix completion tasks, which occur in like say recommendation systems and so on. And the interesting phenomenon we observed is that even though like so even if we don't constrain the U and B matrices to smaller rank or introduce any additional form of regularization, the interesting phenomenon we observed is that both in experiments and some very limited theoretical settings, when we simply do gradient descent or gradient descent on this factorized formulation, we converge to solutions which minimize something called a nuclear norm of the resulting matrix. So we don't have any regularization in the original problem or rank constraint. We simply do gradient descent on the factorized formulation and look at what is the final matrix we end up with. And both empirically and with some theoretical justification, we could show that this does lead to something like a low rank problem, which is, or more specifically, minimum nuclear norm solution, where the minimizing nuclear norm is previously known to also introduce like low rankness, so it kind of fits in with the theme. And this happens under very specific choices of like hyperparameters. Specifically, this happens when the initialization is very small and also step size is very small. And for theory, we need to quantify what this small means. But empirically, for the purpose of this talk, we'll just say that when we take the initialization to be very close to 0 and step size to be very small, we do observe that we converge to a minimum nuclear norm solution, and a follow-up paper kind of extended our limited theory result to much more general settings with Gaussian measurements. So although we started with the nuclear matrix factorization setting, this result has a special case which is much more easier to understand. So here we go to a new and simpler model than matrix factorization, which is simply a linear least squares problem. So we have an overparameterized least squares problem or an underdetermined setting where beta is a vector I'm trying to estimate, and I want to estimate a beta such that x times beta approximates y. And the problem here is this: x is a fat matrix, so obviously this has many solutions, like modulo, assuming x, the rows of xn are sufficiently independent. This has several solutions. But we can try to understand which solution different optimization problems lead to. And if I just wrote an optimization problem directly in terms of beta, with a simple calculation, we can show that you implicitly converge to a minimum L2 norm solution, even though we didn't add any regularization. But a consequence of this matrix factorization theory is that if you specifically parameterize beta in this weird way, where I take a d-dimensional vector W and multiply it by itself. I will also later discuss a variant where this, of course, can only produce positive beta. I can also later discuss a variant on how to use it for general beta. So we are going to parameterize positive beta as W squared, where its square is element wise, and we are going to minimize the loss function with respect to this specific parameterization. Is the problem clear? So it's a simple least squares loss, except that we are using this weird parameterization with like beta represented as W squared. And a corollary of our previous result shows that if you do infinitesimal initialization and infinitesimal step size, the solution returned by gradient descent is exactly the minimum L1 norm solution. Of all the possible beta it can return, it will return a solution which has minimum L1 norm. And later results also show that like you can get similar results if you don't use square, but a power W power D and so on. We'll come back to this particular model in more detail later on, because this would be kind of important to what I'm talking about today too. So this is kind of interesting because interesting from a understanding point of view. I just want to clarify that many of the time, these optimization algorithms are not necessarily like the best. If you want minimum L1 norm solution, there are better optimization algorithms to achieve minimum L1 norm solution. But in this setting, it kind of throws a light on like two things. One is the fact that when you have over-parameterized optimization problems, the algorithm plays an important role. Using gradient descent on this problem is what leads to minimum L1 norm solution. If I use a different algorithm, it leads to a different solution. And the second important thing, which I will mention, but I'll not talk too much about today, is the fact that like the specific parameterization matters. Even though we're considering just linear models here, representing linear models as beta directly versus W squared changes what kind of solutions you converge to. And this becomes important because like one can ask, why is gradient descent a universally preferred solution? And the catch here is that gradient descent on specific architectures lead to different solutions. So you can fix gradient descent and change the parameterization to get different optimization, different implicit regularization effects. So the architecture does, I mean, if in a neural network context, this parameterization is represented by architecture. So if you think of large neural networks approximating any continuous function, the specific parameterization like convolutions or like transformer models or any of these universal approximators of continuous functions are all you can think of as different approximations of like the class of all functions.
Sorry, can I just, we're getting some audio issues. So I'm just wondering if you can try turning off your video, just see if that helps a bit.
Okay.
Great, thanks.
All right, thank you. All right, so I went into detail about these two results, but these were specifically for squared laws, and one of the reasons is that I'll be using these as a basis for the rest of my talk. But there's been a lot of follow-up work on this, specifically like in the context of extending to classification problems, which I won't talk about much, but just to give a lay of the land. So classification problems, specifically if we use optimized losses such as like exponential laws or logistic laws, which are commonly used, you need to do a slightly different kind of analysis, which sometimes gives us interesting regimes to work with. And specifically, like the one issue in classification problem is that with exponential or logistic laws, is that these losses don't have finite minimizers. So if you have a linearly separable data and then do a logistic regression, there is, without regularization, there is no finite minimizer for the problem. And in other words, all global minimizers are at infinity, even though this is a convex problem. So if I run gradient descent on this problem, eventually you will diverge to infinity. And so you need to ask different questions in terms of what is the classification decision boundary you converge to. And there has been a series of work which generalized much beyond like linear models, and also like initial work showed that like how you can represent different linear networks and get different kinds of implicit biases. But a more recent set of works kind of established that you converge to some interesting biases even for nonlinear models. And this is a broad class of homogeneous models. I'll try to come back to this slide in the later point, but I put it here mostly for references and in case people want to look up more in this literature. But going back to square laws, which will be the focus of our talk today. So while we were building this one line of work, few of the groups are building this one line of work on understanding simple models and like trying to generalize to larger models, there is another way to approach theory of neural network, which is start from the largest neural networks possible and try to come down to where we are currently. And this theory was essentially developed also simultaneously, or like or somewhat like offset by a year or so, which is based on what are called neural tangent kernels. So the basic idea is very simple, although the mathematics becomes very like tedious to handle. So the basic idea is that you take any nonlinear function f, which is parameterized by w. So the f takes w and x. X is the input, w are the parameters, and you want to expand it, do a Taylor expansion of f around the initial, let's say an initial value of the parameters w0. So you can do, there is a the function evaluated at w0, then there is a linear term, and then the quadratic terms and other higher order terms. Now, if we stare at this equation, we see that if the gradient descent path, let's say we are doing gradient descent on this function class, and if we somehow establish that the gradient descent path always stays close to the initialization, then we can see that we can ignore the higher order terms and just keep the linear term. Right? And in particular, we can approximate our original nonlinear function by a function which is linear in the parameters. This is still nonlinear in the inputs, but it is linear in the parameters. So I'm going to denote the approximated linear function as f bar. And this is simply a first order approximation of our original problem. And what I'll be calling as kernel regime in this talk is essentially the settings in which gradient descent iterates w of t, which is like the functions generated by doing gradient descent on the original nonlinear problem, are very close, are exactly equal to, or at least very close to the functions generated by this linear approximation. Okay. Or I call it kernel because this is essentially a kernel machine. Although I see it linear, it's just linear in the parameters, not in the inputs. So in particular, it is a linear model over a modified feature map, where the modified feature map is given by the gradient of this nonlinear function at initialization. And this corresponds to a kernel, which we call as neural tangent kernel, which essentially establishes a similarity between two input points, x and x prime. So why is this line of work interesting? Because once we establish that gradient descent remains in this kernel regime, we know exactly what gradient descent converges to, because linear models are very easy to understand from a gradient descent point of view. And specifically, we know that for squared laws, you converge to something which minimizes the RKHS norm to the initializations while fitting the data. So if there is some initialization of this function in the function space, and then you converge to a minimum RKHS norm with respect to this neural tangent kernel. And for a squared for classification problem with exponential tail losses, we know that you converge to something which corresponds to maximum margin separator with respect to this RKHS norm. So once we establish that gradient descent is in the kernel regime, we know a full picture of what gradient descent converges to, and all we need to do is like analyze gradient descent for linear models. Right. So the question is, when does gradient descent or gradient flow, which is an infinitesimal step size version of gradient descent, remain in the kernel regime? And some of the early work, which in just 2 years has generated a lot of literature, essentially established this kind of a kernel behavior when you take very large neural networks, essentially neural networks with width going to infinity. But a follow-up work kind of took a step back and showed that most function classes, which is essentially most continuously differentiable nice function classes, the kernel behavior is always observed. It doesn't have to be large networks. The kernel behavior is always observed in certain regime. In particular, the regime is when the scale of the output goes to infinity. The scale of the output is something hard to explain, but if we restrict to what are called homogeneous models, which is essentially like if you scale the parameters by alpha, this final function gets scaled by some scalar function of alpha. So for such homogeneous models, essentially the work by Chisat, Alain, and Bach established that the kernel regime is attained when the scale of the initialization goes to infinity. What does it mean? If I initialize at say I have parameters w, I initialize to some fixed vector, and then take a sequence of models which are initialized with the scaling of this vector. As the scaling goes to infinity, you converge to, these work established that if the scaling is large enough, then you start approximating a kernel model. So this is in turn applicable for any model, including linear models. In particular, to state it more formally, if I have any homogeneous model, like and look at the gradient flow path when the model is initialized with a scale of alpha. Scale of alpha, I mean, because we are talking about asymptotics, it only like you take a constant vector and then scale it by alpha with alpha as a parameter. And look at the limit when like the function goes to infinity and the scale of the alpha goes to infinity. Then in that limit, the theorem establishes that the gradient flow path is exactly traced also by this linearized model. As a consequence, if we specifically for simplicity, if we initialize at an unbiased initialization, if your initial predictions are 0, then the solution we converge to is the minimum RKHS norm solution. Okay. And this line of work is in turn like contradictory. So this is in turn because it's applicable for any homogeneous model. This is specifically also applicable for linear models like matrix factorization and like the square parameterization we converged earlier. But this seems to create an apparent contradiction, because on one hand we say that like under certain regimes we converge to a minimum RKHS norm solution. On the other hand, we did see examples where for homogeneous models under certain other regimes, you converge to solutions like minimum L1 norm or minimum nuclear norm, which cannot be represented by RKHS norms. In particular, the second example of minimizing over the linear model with squared parameterization, we know that you converge to a minimum L1 norm, which cannot be represented by an RKHS norm. So there is a transition away from a kernel regime under certain other settings. And the key controlling factor, at least in this example, is the initialization scale. In particular, we see that the scale of initialization needs to go to infinity for the kernel regime to kick in, whereas in order to get minimum L1 norm solution, you need the scale of initialization to go to 0. And that seems to be the key controlling factor, at least for this problem. And we set out to also, in more recent works, we set out to understand how does the transition happen between these two regimes for different hyperparameter choices, in particular the initialization scale. And for that, we restrict to this very basic linear model, where our inputs are, our model is essentially a linear model, but we also want to represent both positive and negative vectors. So instead of writing beta as W square, we write it as W1 square minus W2 square. So this way, over W, you can represent both positive and negative values of beta. And we again study the same setting where we initialize the parameters, which is both W1 and W2 to alpha times all ones vector. It could be any constant vector. And then we run gradient flow on this problem and study what does gradient flow converge to as we optimize this problem. And we specifically, and in particular, we know the two extremes of this case. When alpha goes to 0, from existing results, we know that you converge to minimum L1 norm solution. When alpha goes to infinity, you get to a minimum L2 norm solution. And in between, we hope to establish some kind of an interpolation. And indeed, we were able to show such an interpolation, but with a very unintuitive regularization. So in particular, for any fixed alpha, we were able to show that you converge to minimizing some function of beta, which is not a norm, and it has a very complicated form. But an easier way to see this is to look at the visualization of how this Q function looks like. So it essentially minimizes some kind of a regularizer on each coordinate, and this regularizer looks like an L1 norm as Z, which is an inversely proportional to alpha, or rather alpha goes to 0, Z goes to infinity, and it starts looking like an L1 regularizer. And closer to 0, it starts looking like an L2 regularizer. So in particular, this does give us an interpolation between L1 and L2. But a more interesting aspect of it is it also tells us how quickly we get to these L1 and L2 regimes. And in particular, it points out some key difficulties why hyperparameter tuning is painful, is showing that to get to kernel regime, you pretty much can get to it by having a polynomially large initialization. But to get to this L1 regime, you need to go to exponentially small initialization in the worst case. And in many other cases, we need to fine tune this very carefully in order to be on the edge of reaching the L1 norm regime, which is the deep regime. So I'm running out of time, so I don't have too much time to go into the other aspects of it. So like we said, initialization is one aspect which, fine-grained analysis of this form lets us analyze, lets us understand how the transition happened and why these hyperparameter tunings are painful to do and what regimes we'll be looking at. But it's also interesting to see how the effect changes with other hyperparameters. Specifically, we can look at a version of depth on this model, where instead of doing W square, we do W power D as a parameterization. And in this case, we again see interpolation between L1 and L2 norm. But the interesting aspect here, apart from complicated, besides the complicated expressions, the interesting aspect is that you converge to a minimum L1 norm solution at a much lower, much more easily. So the depth in some sense takes the exponential dependence on initialization to something polynomial. So much more easily, you converge to a minimum L1 norm solution with higher depth. Similarly, just take the last minute, I can also stop if you want to for questions.
Why don't you summarize, and then we may not have time for questions, but.
Okay, so just to summarize, we can also study this in a width regime, and there are some interesting behaviors where we can see that even if initialization scale goes to 0, if we have a large enough width, it amplifies the initialization scale, and you can get kernel regime even in very weird settings. So I wouldn't do justice to the slide, but I would leave it here for references again. And we can, for even going back to the matrix factorization problem, we can see this transition from minimizing nuclear norm, which is the deep regime, versus minimizing the Frobenius norm, which in this case is the NTK kernel regime for this problem. And to summarize, we did see a specific simple example where the optimization flow, optimization bias, or the implicit bias from gradient flow, transitions from kernel to deep regime based on the scale of initialization. But a larger goal of this line of work is to understand how this transition could depend on a bunch of combination of initialization, architectural choices, learning rate, and so on. Thank you for your attention. Sorry for going over time.
Thank you. Very interesting. I think maybe we can sneak in one quick question. So I guess maybe just for context, do you have a sense of, in practice, whether we're running modern deep networks in the kernel or the rich regime, and how that impacts the performance?
Right. That has been also empirically studied. Besides our problems, it has also been empirically studied that when we use this kernel approximation, you don't really get good performance. And in that sense, we do believe that there are at least some deep learning models which work in non-kernel regime, but some of our recent work kind of suggests that going all the way to deep regime, the extremes of deep regime, which we have been analyzing, the asymptotic regimes, might be very hard. So we might be operating in some transitional regime, and that's one other reason studying this transitional regime is really important. And we don't have explicit theory for what specific neural networks we use, which regime the specific neural networks we use in practice depend on, but there is enough empirical and theoretical evidence to show that it is possibly operating either in the transition or in the deep regime, and at least significantly away from kernel regime.
Okay, well, thank you very much. So now we'll move on to our next speaker, Suyun Chung, postdoctoral researcher at Columbia University. And she'll be talking about emergence of separable manifolds in deep neural networks and the brain.
Hi, can you hear me?
Yes, we can hear you.
Great. Hi, thanks for the invitation. So today I'll talk about an interesting geometry-based probing techniques to study the internal representations of deep networks and potentially neural representations as well. So the motivation for this work comes from invariant object recognition, which refers to the brain's ability to distinguish between—
I'm sorry, Soo-Yeon, we actually don't see you on the camera. I don't know if it's gotten turned somehow, but—
Oh, yeah, sure.
I think it looks like, oh, you were just in, it was in your background. That's what it was. It decided you were all background.
Nice. But can you now see me?
Yes.
Yeah, great, perfect. Yeah, so so the motivation comes from invariant object recognition and the fact that we're able to recognize objects despite the immense amount of variabilities that exist in the stimulus space, like size, orientation, or position, or background context. And from the perspective of the neural population, this becomes the problem of object manifolds. So more specifically, if a set of neurons are responding to two different objects, and these neurons are tuned differently to these different types of objects, for example, a dog versus a cat, and they become 2 points in this high-dimensional neural vector space. But as these objects have variabilities, they become two different object manifolds because these representations move around as the variabilities are introduced in the stimulus space. Now, in the feed-forward visual hierarchy, it's been suggested that this separation can arise by layers of nonlinear transformations to increase linear separability. This was first suggested in a paper by Jim DiCarlo and David Cox in 2007. And similar ideas have been suggested in deep network theories that object manifolds are entangled to become more linearly separable across the deep hierarchy. So untangling here refers to reformatting manifolds or object manifolds across the layers to increase linear separability. In this perspective, object recognition with stimulus variabilities amounts to positioning a decision hyperplane between two different object manifolds, which is determined by a direction vector W, normal to the hyperplane, that is equivalent to the linear readout weight on the activity. Now, this leads to the question of how we can quantify and formalize the linear separability of object manifolds and their geometry. So to answer this, we developed a theory of manifold capacity, which is a generalization of perceptron capacity, which is originally for discrete points, but now to object manifolds, as a theoretical tool to assess the manifold representations in deep networks. And this is a work that's done with Chaim Sompolinsky and Dan Lee. Now, so for the rest of the talk, I'll talk first briefly about the theory and the summary of the theory and recent applications of this theory, which turns into a probing technique to visual and auditory and language deep networks. Now, before talking about the details of the theory, first I wanted to define what we mean by object manifolds mathematically, or manifold-like object representations. So let's say we're in n-dimensional ambient space. So that means we have n-dimensional features or n-dimensional units that we want to probe. And these object manifolds are defined by the different categories that we want to classify, and they occupy d-dimensional subspace. And each point on an object manifold is can be summarized as a sum of the center of the object manifold plus the linear sum of the basis vectors, where there are d of them, and the shape parameter s. And the different types of object manifolds can be determined or parameterized by the function of the shape parameter s. We're considering p of the number P for the number of manifolds or number of categories. So if P is 100, that means we're considering 100 different classes, like C bar 100. And these object manifolds do not have to be smooth. I just have to emphasize that because the term manifold sometimes implies that there's an implication in mathematics, but here we're using it more in the sense of there's a subspace that's occupying in the high dimensional space. So you can have point clouds or data clouds, and the convex hull of the data cloud is what we call an object manifold here. And in order to characterize the capacity, we make statistical assumptions about these manifolds, namely that the centers of these object manifolds are randomly oriented, and the subspaces of the object manifolds are also random. And that's the initial set of results on the capacity. Although later on, we also take the correlations between these manifolds into account to apply on the real data. So I'll talk about that briefly. So first, what do I mean by capacity of object manifolds? So this is similar to the perceptron capacity, except where the counting units for the capacity is now in terms of the class manifolds. So if the object manifolds have roughly this kind of geometry, and if you have a few number of categories, then it's easy to separate them. But as you put in more and more of object manifolds, the possible linear separating solution under the binary dichotomy classification reduces. You have fewer solutions, and after some point, it becomes hard to separate them on average. So the point where you can't find a linearly separating solution, that's what we define as the capacity of object manifolds. So that's what we mean by manifold capacity, manifold classification capacity. That is the maximum load, which is P over N, where P is the number of linearly classifiable categories or object manifolds, divided by N, where N is an ambient dimension, where most of these dichotomies of the manifolds are linearly separable. Now, the next question for the theory is how the geometry of these object manifolds are related to manifold capacity. And to do this, we use the tool from statistical mechanics to compute the volume of the solution. So here is a similar picture where we're separating between different spheres, and you can see that the space of solutions, linearly separating solutions are high, but it becomes smaller as you have more manifolds, and it becomes the volume of solution becomes zero as you approach the critical capacity. And to compute the capacity, what you have to do is to explicitly write down the volume of the solution as a function of the geometry of an object manifold. And to do this, we borrow the tool from StatMech called replica trick. Now, what's different from the previous theory on the points is that when you express the expression for the volume of the solution, what goes into this term that counts the qualifying region in the volume in the space of solutions is previously for the discrete points, it was the distance between the discrete point and the separating hyperplane. But as we are considering object manifold, we express the worst point or the point that's closest to the hyperplane on a specific manifold. And it turns out that this technique allows you to express the manifold capacity for general shaped object manifolds as a function of the size of an object manifold and the dimension of an object manifold, and an imposed margin for the linear separation. So then so it's and here I'm showing the summary of the theory that is for a general shaped manifold, the capacity, which is often referred to as an alpha, can be written in terms of the capacity of an L2 ball, which I'll talk about in a minute, where the radius and dimension of the general shaped manifold can be defined for the general shaped manifold. So before talking about the general shaped manifold, I should also emphasize that for the spherical shapes or L2 balls, you can actually analytically write down the capacity for L2 balls as a function of radius and dimension of the spheres or L2 balls with the imposed margin, and it's a pretty crisp form. And you can get a pretty good intuition about the relationship between the object manifold capacity and the radius and the dimension of each one of these object manifolds. And what we're seeing here is the theoretical prediction, which is a line here, matching the simulation capacities. I should also mention that this object manifold capacity can be also measured empirically by simply assigning random labels to each manifolds and reducing or increasing the feature dimension and finding the critical dimension where the fraction of the linear separating solution is roughly 50%. So the markers that you see here are the ground truth or simulation capacity, and the line here is a theoretical capacity. And what you see here is that if you fix the radius of the L2 balls the same, then as you increase the dimension of the L2 balls, the capacity reduces. So the higher dimensional object manifolds are harder to separate. That's generally what we're seeing here. What we're seeing on the right-hand side of the figure is as you increase the radius of an object manifold, the capacity also reduces. So if you want to have a higher object manifold capacity, you need to lower the object manifold dimension and object manifold radius. And then what we're seeing in this particular slide is a result from simple spherical L2 shaped balls. Now, so what I think what I should also emphasize that so using the results that we get from the L2 ball theory, what we can then do is to generalize the expression for the capacity of general shaped manifolds, and the form of the general manifold capacity actually turns out to be very similar to the capacity for L2 ball. Then that actually allows you to define the measure for the radius and dimension of an arbitrarily shaped object manifold. And without going into too much of a detail for the time constraint, what I wanted to mention is that the radius and dimension of these object manifolds are determined by what we call anchor points on an object manifold, and they're basically like the points that are representative for the linear classification. So similar to support vectors, but since we're considering object manifolds, we could have the entire subspace of anchor points, for example. And then the object radius and object dimension properties, so they basically capture the statistics of these anchor points in terms of their size and the dimensions that are observed by the linear classifying hyperplane. So and so far this was the theory that captures the capacity for L2 spherical balls and the general shaped manifolds in random positions. But in reality, the data also has the correlations. So recently we took the correlations between the data into account. And what we find is that the correlations between the centers of these objects tend to reduce the capacity, and they're often low rank. And this can be basically taken into account for the theory. And for the rest of the talk, I will refer to, I will talk about the center correlation. So yeah, the center correlation that I will refer to is basically the average of the pairwise overlap between the manifold centers. And the summary of the theory basically comes down to 4 of these properties. And this is basically all you need to remember to understand the rest of the talk that is more exciting on applications. But yeah, first, the manifold capacity, which is a measure for how many object manifolds you can linearly classify per feature dimension, such that the manifold dichotomies are linearly separable. And this captures the linear separability of object manifolds, or you could also think of it as a storage capacity of not patterns, but object classes. So how much of an object variable object information is encoded in the distributed representation. So that's the manifold capacity. And manifold dimension and manifold radius. And the correlations between the locations of these object manifolds, so these 4 properties are theoretically linked in such a way that the capacity can be predicted by the geometrical properties of these object manifolds. And they're related in such a way that when you're in a highly tangled and bad representation, the capacity is low, and that tends to be correlated with a larger object manifold dimension and larger object manifold radius and higher correlations. And if you want to drive the representation to be highly untangled and separated, you need to reduce these 3 properties. So this is basically the summary of the theory. And without more details, we'll go to the applications. First, we'll talk about how object manifolds emerge in the visual deep networks. So we use an ImageNet to define 2 different types of object manifolds. One is a point cloud manifold, where object manifolds correspond to the different classes in ImageNet, and the points or vectors within the object manifold are different examples. Another object manifold that we define is a fine transformation manifold, which is starting with one image, and you apply a fine transformations to get a smooth and small manifold, and this is kind of reflective of the data augmentations that you do on a deep net. And then you run these images on conventional CNN, and you can extract the features from every layer of the network and start analyzing it with this metric. So first, before going to the geometry, I wanted to also mention that the theoretical capacity that we get from this replica theory matches the empirical manifold capacity pretty well. So that's one thing that we want to just show at least. And you can then see how the manifold capacities are changing across the layers of these deep network. And so here it's an AlexNet, and you can see that they improve across the layers of the deep network representations. So left is point cloud manifold and right is smooth manifold, and they both improve. And this is probably quite similar to what you would get if you just train a linear classifier on top of the deep net and then try to get the accuracy. It's known as a linear probing method. But what we can do with this metric now is ask the question of why these manifold capacities are improving across layers. And now we can answer that question by looking at the geometrical properties. So this is a manifold capacity improving across layers that we saw, and you can now tell that this is because the dimensionalities of these object manifolds are reducing, as well as the manifold radius and the center correlations between the object manifolds. Now, there are a lot of repeating motifs within these conventional deep nets. Here, we're looking at AlexNet, but you can find a similar motif in BGZ16. And then you can start to analyze what is an effect of each network motif or the nonlinearities that are used a lot on the geometry of these object manifolds. And what you can see is that this is an analysis on the pre-trained network, and then just on all of the ReLU layers, and then before and after. So that's why we're showing the delta. So this is a change in the object dimension, change in the object radius, and a change in center correlations. And if you want to go to the direction where you're improving the object capacity, object manifold capacity, you basically want to reduce all of these properties. And so you want to be in the negative quadrant. But what we're seeing is that after a single layer of ReLU, there's a trade-off. So it's reducing the correlation, but it's increasing the dimension. Here also, this is, maybe here in the max pooling layer, this is decreasing the dimensionality and radius, but it's increasing correlation. There seems to be some trade-off between these properties. But when you combine these layers together, the function of these clusters of the layers become good in the sense that the effect of these motifs are such that they're in the negative quadrant. But overall, what we're seeing here is that when there's typically some trade-off when you just focus on one layer. When you combine them, the representations change in such a way that it improves manifold capacity. This metric is not just for a deep net, so you can also use it to analyze the neural representations. So here we're using the neural activities from V4 and IT regions of the macaque monkey, and you can see that the manifold capacities are also improving across the ventral stream hierarchy. And that's and you also see that there's a reduction in the dimension and radius of these object manifolds. We can also analyze how these properties, how this untangling happens over the course of the time. So you can use this task-relevant geometrical tool as a measure for characterizing high-dimensional neural population, and use it to compare the representations between the monkey neural data with the deep network. Well, this is an ongoing work. Now, I'll quickly go over the applications in other modalities. So this metric doesn't it doesn't care about the modalities. You can apply it on any representations that have well-defined categories. So what we went ahead and did was to take the conventional speech recognition models. This is a deep recurrent network where the input is coming in the form of a sequence of spectrograms, and the network basically transcribes the text. But here you can also define word manifolds, for example, because this deep speech network is hearing spoken language, and it transcribes the text, and it's done, and then you can define the words in different contexts and spoken by different speakers. And what we find is that there's very similar untangling observed in the speech recognition network. So you can see that the word manifolds are emerging across the layers of the deep net. And I should mention that this is a network that's not explicitly trained to recognize words. It's a transcription network, but you can see that there's an emergence of object information of words. How that's related to the geometry seems to be also very similar to vision. So that's the emergence of capacity seems to be due to the reduction in radius and dimension and stellar correlations. Interestingly, you can also probe the manifolds defined by phonemes and part of speech. They also seem to emerge in the same network as well. And you can see the role of recurrence by analyzing the emergence of manifold capacity across time steps, which you can see by doing a dimensionality reduction technique. These are the different words, and then you can see that they separate and come back over the course of the time. But this metric allows you to quantify how they emerge and also across different layers. And then this is, lastly, similarly, you can also use this technique to probe the internal representations of the language models. So here is our first attempt at doing a proof of concept kind of work on probing how language manifolds might emerge in transformer networks, where initially the networks are the input sequence has the mask data, and the network is trained to predict the token that's been masked, and you can see that across the course of the layers of the transformer architecture hierarchy, there's an emergence of a lot of interesting linguistical object manifolds observed by the capacity. What's interesting is that there is one linguistical tag that doesn't seem to emerge, which is dependency depth, and this is very specific to syntax. And it seems that this is an interesting result because the linguistical tags that are defined by the categories, they all seem to be emerging across the layers, but the tag that has transitive information like the depth of a tree, that doesn't actually seem to emerge. And it probably is because the capacity manifolds are about classifications and it doesn't really capture the relative numbers in the tags. In any case, this improvement in the capacity is due to the similar kind of reduction in radius and a reduction in the dimensionalities, except for the dependency depth and the reduction in the center correlations. So we can also use this technique to probe the internal representations of language models, which is somewhat interesting. It's coming out in ICML soon. So to summarize, we generalize the step mech theory of linear classification of points to that of general randomly oriented manifolds. And the capacity of category manifolds measures the invariant object information in features. And this is predicted by the effective size, radius, dimensionality, and correlation structure of these perceptual manifolds. And we've shown that you could use this in the vision and speech and language models, but there's also a lot of exciting future applications and perhaps probing learning dynamics, checking the untangling in motor motifs or other sensory modalities. So there's a lot of exciting future work. And then I thank my collaborators and mentors, especially Heinz Sobolinski and Dan Lee and Uri Cohen.
Great.
That's the end of my talk.
Thank you very much. I know I have many questions, but unfortunately, I think due to time, we're going to have to take those on Slack. So if you do have questions, you can just post those on Slack. And otherwise, I think we'll have to move to our next speaker. Stefan, can you hear me?
Yeah. You can hear
All
me?
right. Yes, perfect.
Good. So I'm going to share the screen.
All right. So our next speaker will be Stéphane Mallat, the data science chair at the Collège de France, and he will be speaking about multi-scale models for deep neural networks.
Thanks for this invitation. So yes, I'll be giving a point of view on deep neural networks, which is not so much related with the optimization issues as was presented by the first two talks, but rather trying to understand the properties of the architecture. So in that sense, it will be a bit more related to the talk of Si-Yun Chung, and also what we know a bit about neuroscience. So the structure of deep convolutional neural networks, I suppose you all know them, and I'll describe it here in the case of an image, which is an input. So you have these linear operators, which are convolutions, followed by these nonlinearities, which are the ReLU, that may also include a bias here. And then these convolution operators are applied on each channel of the subsequent layers to produce the output on one point. Then they are translated in order to get a convolution. And like that, you'll get the next layer. Now, when you go from one layer to the other, you have also a subsampling operation, which may not happen at each layer, but here I put it at each layer, so that ultimately, in the last layer, you will get a neural network where the spatial variable has essentially totally disappeared. And then the miracle is that with a linear operator, and in the case of classification, a softmax, you can get very good classifications for wide range of classifiers, for wide range of problems. Now, there are a number of things that appears in these networks. The first one is that on the first layer, you almost systematically see convolution kernels that looks like wavelets, small wave with small support. I'll come back to that. And also, as you go deeper and deeper, you aggregate the information over a wider and wider range of in the original image. So you can view this deep axis as a kind of scale axis, which will accumulate information at different scale. So the main question is to understand why you have this concentration phenomena in the last layer, where each of the class are going to be distinguished linearly so that a simple logistic classifier can obtain a remarkable result. So question, how do you get these concentration and separation? Now, if you look in the visual cortex, we all know that you have these cells, which are called simple cells, which were initially discovered by Hubel and Wiesel, which essentially behave like wavelets. If you look in the hypercolumn of the visual cortex, you can see wavelets with different orientation. That comes from a physiological publications, and different scale as you get closer to the center of these hypercolumn structures. And then when you go to higher visual areas like V2 up till V4, you observe complex cells which are more and more invariants up to V4 and IT. And the relation with deep nets were demonstrated by a number of authors, among which Di Carlo. Now, if you look in audio, you see a similar structure. Again, in the first layer, in that case in the cochlea, you have something that looks like a wavelet transform, which separates the information within different frequency bands, which are again dilated, and then that's transmitted to the audio cortex. So the question is, why do you have these wavelets which appear at early stage, both of vision and audition? And also within deep networks, what's the reasons? And also, what do you need to learn with these deep networks? So the first part of the talk, I will be discussing the construction of these operators, which allows to concentrate the information in order to obtain good classification without any learning, to see how far we can go. And we'll see that very naturally you see appearing wavelets, rectifier, and architectures which are similar to deep network architecture, just from the type of priors that we have on images. Now, these concentration operators, which are constructed just from priors, are not enough in order to obtain good classification results on very complex image database like the one that you see in ImageNet, which includes millions of images, thousands of classes. So you need to learn, but the question is really, what do you need to learn and what is learned? What's the nature, mathematical nature of what is being learned? And one point that I'll be showing is that really what you need to learn is the transformation along the channels, not spatially. Essentially, spatially, the filters can all be taken to be wavelets, but along the channel, the phenomena is much more complex. So let me begin with the approach of the problem without any learning. So the problem is to define a map, this phi of x, which will be the last layer of the neural network, which is able to concentrate the information. So for any class Y, you want that phi of x concentrate on a very small zone that was the corresponding manifold that were more and more concentrated, as we saw in the previous talk. And you would like to understand what kind of mathematics would allow you to obtain such a concentration. Now, of course, there is one element which is very important in many object recognition phenomena. You have a translation invariant problem. If you translate your object, you recognize it as the same object. Now, this will allow us to compute this concentration through spatial averaging. As you know, if you have weakly correlated random variable, if you begin to average them with the central limit theorem, you're going to get a concentration. Now, you have something else that appears is that images have many sources of variability, including deformation. And when you have small deformations, you can recognize essentially the same kind of object, whatever small deformation. Here you can see it in the case of paintings. Now, in order to be stable to these deformation, what we're going to see is that the scale separation provided by wavelets is a very important element. Now, in this first phase, as I said, we're not going to learn. So you still need to separate different information for different class. So keep as much information as possible. And that will lead us to a deep network kind of architecture. So let me look at these wavelets. As I mentioned, these wavelets in the case of the visual cortex looks like localized small sine wave. You can have like a cosine or a sine wave, which have different phases. And the wavelets that you encounter may have different angles. So they are basically rotated, as you can see here, and are going to appear at different scale. 2 to the j here is what is going to scale the support of your filter, of your wavelet. Now, what is a wavelet transform? It's very simply a convolution of your input image with the wavelet, which is shown here. And because the wavelet has a zero average, basically it's going to compute kind of local contrast on your image. So the output is going to be very sparse, essentially non-zero whenever you have a strong transition. Now, if you compute a wavelet transform with all rotation, all dilations, and you construct well your wavelet, you are going to get a representation which is essentially complete. You can recover the signal from all these wavelet coefficients and from the image average, and stable. You have a conservation of energy. So that's how it looks like. It had been very much studied, in particular for compression denoising in the 90s. And you have this fast wavelet transform algorithm, which first computes the fine scale, the average, from which you compute the next scale, the next scale. So that looks like the first very simple structure, which has some kind of similarities with the cascade of a neural net. Now, you want to concentrate the information. As I said, if you can average your variables, if you have some weak the connection between your variables, you'll have a tendency to concentrate. Okay, so if you average locally, you are going to preserve a bit of information. If you average globally, you are essentially just get the average and lose all the information. So where is the information that is lost? It's the high frequencies. And the high frequencies, I show it in one dimension, will be carried by the wavelet coefficients, which oscillates. But because these coefficients oscillate, you cannot just average them to concentrate the information because you are just going to get a zero. If you put a rectifier, everything gets positive. And now if you average the information, you are going to get a new set of invariants, which invariant to translation, which is going to give you other information depending now on the frequency and the angle. But the wavelet transform is invertible, not if you average it. When you average, you lose information. So if you want to preserve separability, what you need to do is to again extract the high frequencies where you've applied your averaging. So you get your wavelet coefficient rectified, and now you reapply a high frequency wavelets in order to recover the information that you've lost before. If you want to have an information which again concentrates, you are going to average, but if you don't want to get a zero, you are going to put a rectifier. And here you see appearing the structure of a deep network. Basically, you have a first wavelet transform, the rectification. And then if you want to average it in order to have an output which concentrates well, you need to extract all the other details that you've lost. It's a second wavelet transform. And now these coefficients, if you want to average them, you also need to extract the details and so on. And you see a cascade of these wavelet transforms. So this is a kind of very simple network where you don't learn anything. You just impose that all filters are wavelets, and there is no connection, no learning across the different channels. Here you have the different channel at one leg. Now, one very important result is that because the wavelets are stable to deformation, a deformation is essentially a local change of scale that will appear at different points of the image, which can also be written as a translation that depends upon space. If you look at the output of your network, which is here called the scattering transform, if you deform the signal, the transformation of the deformed signal is going to be very similar to the transformation of the original signal up to the size of the deformation, which is here given by the gradient of the deformation function here, tau. So you have this stability to deformation, which essentially you linearize the small deformation, which will allow you to preserve the concentration, whatever small deformation will come in. So if you apply that directly to classification, you have your network, which again, you don't learn anything, you don't have any connection across channels, which produce a representation where you have in the different channel, the different frequency, different phase, and then you put a logistic linear classifier at the end. That will work well if you have a simple problem like digit classification, textures, but it's not going to work if you have a very complex problem like ImageNet, where the error is of the order of 40%, whereas in the case of ImageNet, the error is twice smaller with LXNet, or even much smaller for ResNet. So the question now is, what is learned along the channels? Now, the first idea that comes to mind is that the learning is going to operate in order to extract patterns, sparse patterns that may occur within the image. Now, in mathematics, there's a relatively standard way to think in terms of sparse patterns, is to store these patterns in a dictionary, which is a big redundant matrix. And if you want to represent X as a linear combination of a few patterns, you are going to create a sparse code, multiply your dictionary by this sparse code, which amounts to select few patterns to represent X. Now, what is this sparse code? The sparse code can be written as a solution of an L1 minimization problem, where you impose that X is close to the linear combination of your few patterns, and you impose that your sparse code is sparse by putting here an L1 node. Now, there are iterative algorithms to solve that, and you can write that as a network, which is here this D-sparse network, which is essentially an implementation of an iterative thresholding algorithm with a ReLU and bias at each layer. Now, this network has only one matrix, D, which is repeated within each of the layer, and then the final classifier. So if you want to learn this matrix, basically, you are going to do a supervised learning where you learn both the matrix and the classifier in order to minimize the loss due to the prediction of the class and the error relatively to the true class. So basically, if you want to do that, you'll need about 12 layers in order to converge to a sparse code, which is precise. And you can try that kind of thing for image classification. Now, if you try that on ImageNet, as I said, AlexNet, that was 2012, had an error of about 20%. If you do the scattering transform alone, which doesn't use any learning, the error is about 40%. On the scattering domain, so here in this domain, you've imposed some translation invariants. You are stable to deformation. If you learn patterns within this domain, with this network, you obtain now a matrix which is very sparse, about 3% non-zero coefficient. You learn jointly the classifier and this matrix D, which is going to do the sparsification, and boom, the error jumps from 40 to 18%, which is a bit better than ImageNet. So the question now is why? Why this single matrix can divide by 2 the error, and what is the nature of this reduction? So the first idea that comes to mind is to say, okay, you built a sparse dictionary. It works well because you've selected few discriminative patterns for classification. Now, we all do a lot of theories out of few experiments, and maybe one lack on this domain is to have a way to check whether the theory is right or not. So let's check it here. So if it's sparse, one thing we can do is from the sparse code reconstruct an approximation of the input with the dictionary D. We said DZ should be an approximation of the input. This is not sparse at all. We're going to learn again the classifier together with D. If we look at the error, it's still very good. So that means we've destroyed completely sparsity, we've destroyed completely the idea of features because of the reconstruction. That shows that sparsity is not the source of improvement. If we look at the difference between the approximation and the original, we realize that we've eliminated a lot of information because we use a very large threshold that was learned, a very large bias. So next idea, maybe the improvement comes from the fact that in fact, we've removed some cluttered information, some kind of noise through this very large bias in this dictionary and through the explaining away mechanism of sparse coding, we basically remove the clutter but preserve the information. So explaining away, many people speak about that to analyze the performance of deep learning. Let's remove the explaining away. So the 12 layers that I had here of the sparse code, which allows to explain, to implement this explaining away, I replace it with one layer, still a convolutional dictionary along the channel, and a bias. And we learn the dictionary, the bias, but there is no explaining away, just a projection in this matrix and the classifier. The error is the same, even a bit better. So no explaining away is needed, at least for ImageNet. Now, do we need to have a very large bias in order to have a sparse code? No. You reduce the bias The output here is not going to be sparse anymore. The error is a bit worse, but still stay of the same order. So it's not either the sparsity. However, if you remove the ReLU here, the error is multiplied by 2. So immediately the error jumps. So obviously the ReLU is fundamental. Okay, so what about the ReLU? What is its role? Now, a ReLU, you can view it as having two functions. It has the ability to separate phase information and to get amplitude information. So in order to see whether phase is important, we did a simple test, replace the ReLU by a sign function. So the output will just be 1 or -1. So it's an information about phase. So, and we're going to do it here first with a simple linear classifier. So if you just do a scattering, the error is about 55%. If you do, you learn your matrix with no explaining away and a ReLU, you get here an error of about 27%. If you use the same matrix, but you replace the ReLU by just the sign, you get about 2% worse. So but still the improvement was of the order of 25%. So in this case, what looks like is that the phase is extremely important. And if you eliminate all the amplitude information, which is about building a very strong invariant, you get a big improvement relatively to a direct linear classifier. Now, why is that so? Not completely clear. The only thing is that the first layers before, which was the scattering transform, eliminates the variability to translation, so stabilize the phase very much. Now, up till now, we are getting performance of the order of 20%. Can we go to residual ResNet performance with that kind of architecture? The answer is yes. You don't learn anything in space. In space, you just apply the wavelets, which we observe in the visual cortex or in the auditory cortex. You just learn along the channel. Each time you learn a linear transformation along the channel. So the only thing that we're going to learn are these 1-1 convolutions just along the channels. If you do that so that the last layer has only 1 pixels because you subsample your softmax, you essentially get the type of result you get with a ResNet. Here we have an architecture with only 6 layers. The ResNet with 18 layers gets 1% less. And if you put 50 layers, you get even better. Now, what is that showing? It's showing that essentially the spatial information is gathered with these multi-scale aggregation performed with wavelets. The learning is across the channel, and that's where we essentially don't understand well mathematically what's happening. One element that comes out is that phase is very important. So let me conclude on that. First thing, it is possible to a priori have good ideas about these concentration operators, in other these transformations that are done by these networks, and their harmonic analysis is helping a lot because you have translation, you have the Fourier transform coming in, scale separations, and so on. Wavelets also appear in neurophysiology. They seem to be enough for spatial filtering, so that's at least one stable point to look at these things. What is interesting is this phase phenomenon. It seems very important to understand the effect of ReLU along channels. And phase is something that has been very much discarded in mathematics, in harmonic analysis. Most of research was trying to work out of the amplitude information to threshold, to denoise, and so on. Now, what looks like is that what you learn across channel is extremely important to obtain this concentration and separation that we observe in neural net. One of the things I would advocate here is to build controlled experiments for mathematics. We have a tendency to build theories of neural nets with all kind of tools, usually the one that we understand well, in my case, harmonic analysis. But there is a bit of lack of counter examples to evaluate these theories. So I tried to do a little bit of that today, but I think that's something which is important in order to be able to move on and try to see what mathematics are not relevant and what are potentially relevant. Thanks very much.
Thank you. If anyone has questions, you can input that into the Q&A part of your screen. But maybe I can kick off. So I'm just wondering, it sounds like you say you don't know that you have any insight into it, but if you've looked at what those matrices that go across channels seem to look like, just as an empirical matter after training, is there any structure you've been able to pull out from them?
Oh, the matrices. We looked at them, and no, it was not so easy. The kind of thing that you can do is to see what responds to these matrices, which are the kind of thing that has been done before. And you do recover the kind of results, you are selective to patterns and so on. But what is very difficult, one of the hypotheses we had was that these matrices are building invariants over other types of groups and maybe could be interpreted as convolutions over other type of groups. But what we are currently lacking right now is the ability to learn groups that would be related to matrices. This is a very interesting mathematical problem. And right now, we don't have the tool to learn these groups if these groups do exist. So the short answer is, this is a very nice problem. I think it's a nice problem for everybody right now.
All right, and a question from Mark van Rossum. Are these networks more robust to adversarial attacks?
Now, that's a very interesting question. One part of the network is more robust. All what we do spatially, the wavelet transform, is unitary, so there is no way you can do, there is no instability related to adversarial. However, along the channels, you learn operators and you do renormalizations. And these renormalizations are equivalent of batch norm renormalization. And because of that, the norm of these operators is not 1, so that a small error can be amplified. So you can get, we didn't test, but I'm sure you can get adversarial example. And one very interesting problem would be to control the norm of these operators in order to try to fight against these adversarial examples. You see that once you have a somewhat simplified architecture, when you just learn these one-to-one convolutional operators, and there are not so many, you can even reduce it to a single one, you can indeed study that kind of problem.
Great, thank you. There are several more questions, but I think we have to move those to the Slack channel. So thank you very much to all the speakers for your talks. And that closes this session. I believe there's now a session on the poster prize winners talks in the other YouTube channel, if you'd like to move over there. And thank you very much.
Thank you to you.
Yeah, thank you everyone. That was fantastic. And I would ask now people who are interested in poster prize talk, winners talks, go to channel 1. Thank you very much.
Bye.
Thank you very much.